baby. It's been a long day, baby. Things ain't been going my way. You know I
A little
need
bonus section for you today. This section I'm calling Local Linear Approximation. It's not in your textbook, but it will come up next year in calculus, I'm sure, so I thought I'd give you a little preview of it this year. So here's what we're going to do. We're going to estimate the value of the square root of 4.2. Now, you could probably do that right now. You know the square root of 4 is 2. This is a little bigger, so maybe you're going to say it's about 2.1 or something like that. That's a good estimate. But we're going to find a method for solving questions of this type. So the first thing to recognize here, I guess I'll write it down, is that whatever our answer is, it's very close to the square root of 4. So we're talking about the square root of 4 here, we're talking about the square root of 4.2 here. So why don't we create a function, we'll put let f of x equal the square root of x. And let's graph that. So you know what the square root of x looks like, right? It is a curve. There's the point 0, 0, there's the point 1, 1, there's the point 4, 2. I'm just approximating this, and there's a point 9, 3. Looks something like this. And the point we're interested in is this point right here, 4. If you go up from that x value 4 until you hit the function, there's the point right there. And if you come over this way, you would be right at the y value of 2. What we're actually interested though is not 4, but a different point, which is 4.2. So if we go straight up from that one, it's going to be a little bit messy here, but hopefully you'll get the sense. Maybe I'll draw this a red point here. And if I was to go over to the left from there, I would want to know, well, what is that value there? It's going to be 2 point something, but exactly how much is it? So this red point right here, this is the actual value of the square root of 4.2. And to tell the truth, we're not going to find that exact point here, that exact value. We're not going to find it, but we're going to find something very, very close to it. How are we going to do that? We're going to do that by drawing the tangent line to this function. Remember, this curve is the function square root of x. So what we're going to do is we're going to draw a tangent line to this function at that blue point right there. The point that we know, right? I know what the square root of 4 is. So here's something I know right there. I'm going to put a tangent line right there. So wait for me. I'm going to draw that tangent line. So here's the tangent line. It's not that I haven't drawn it the best, but I wanted to exaggerate this space a little bit here. If I think I did a perfect tangent line, it would almost go through that red point there, and I don't want it to. So assume this is the tangent line that goes just through that blue point. I know it's not a great drawing. And what we're going to look at is the point that if we extend from this 4.2, we don't stop at the actual value, but we go a little bit higher up to that tangent line. So I'll put a green dot right here. We're going to find the value of that point right here. Now, is that point going to be exactly the same as this question mark one? No, it's going to be higher. But how much higher is it going to be? Very, very tiny amount bigger, right? So we're going to let this tangent line, we're going to use that tangent line to estimate that green point, which is going to be really, really close to the red point, which is the actual value of the square root of 4.2. So notice that this method we're going to use works as long as we pick values that are really, really close to 4 in this case. You wouldn't want it to estimate the value of 10.1, which is way out here somewhere, because at 10.1, the actual amount here, I'm going to put 10.1 here, the actual value you'd want is here. The one that's estimated using the tangent line is way up there, and you can see there's quite a big gap there. So you wouldn't want to estimate too far away from 4, but 4.2 is not that far away, so that should work well. So I'm just going to write in here that this green one, this is our approximate value that we're going to find. And actually what we call it, the approximate value, we call it the linear approximate value. So now what we're going to do is we're going to find the equation of that purple tangent line. Because both the blue and the green line are on that tangent line, it's going to be helpful for us to find the equation of the line. So remember, to get the equation of a line, what you're going to do, maybe what I'll do here is I'll put an arrow and put equation to show we're getting the equation of the tangent line. And remember, to get the equation of a line, you need a slope. Well, we know how to get the slope of this tangent line. We'll do it in just a second. and we also need a point. So here's what we should use. We should use the point 4, 2, this blue one here, right? That one's on the purple tangent line, and it's also on the black function. So we're going to use the point 4, 2, and for the slope, how are we going to get the slope? Well, to get the slope of that purple line right there, we're going to find the derivative of the function, this black function, because when we get the derivative of the black function at that point 4, it will be the slope of the tangent line. That's always what the derivative gives you, the slope of the tangent line. So the slope is going to be equal to f prime of x, but we're actually going to figure it out, f prime of 4. Okay, so now we can put it in slope point form. Slope point form is y minus y1, which is 2, equals m, which is your slope. So we better hit pause here for a second and figure out what is f prime of x first of all. So f prime of x equals, well, remember, square root of x is the same as x to the 1/2. So then the derivative of that is power rule, bring the 1/2 down, x to the negative 1/2. Or the other way you could write that is 1 over 2, this is a flipping negative, comes to the denominator, and 1/2 is the same as root x. So that is what f prime of x. But remember, for the slope, we don't want f prime of x, we want f prime of 4. So f prime of 4 just means plug 4 into here. So you get 1 over 2 times root 4, which is the same as 1 over 2 times 2, or 1 over 4. So there you go. Your slope is 1 over 4. So this is y minus y1 equals m, the slope, and then x minus x1. Well, x value is 4. And then what we tend to do is isolate the y when you do these questions. So move the negative 2 over. So you get 1/4 x minus 4 plus 2. This is great. This can be used to make approximation of square root values close to 4. Right? If we wanted to know what 4.2 is, that's what we actually want to know, the square root of 4.2, we'll plug 4.2 into x. If we wanted to know what the square root is of 4.01, put 4.01 in here. If we want to know what the square root is of 3.87, put 3.87 in there. But notice we only want to pick numbers close to 4. I'll say it again, you wouldn't want to put 10.7 in here or something. It's too far away from 4. So let's go ahead and plug, since this is the one we're actually interested in, let's plug 4.2 in here and we'll get our y value and we'll be done. So y equals 1/4 4.2 minus 4 plus 2. Alright, we're going to end up with decimals here. So why don't we change this to a decimal? Let's make it 0.25 times 4.2 minus 4 is 0.2 plus 2. So y equals 0.25 times 0.2 is 0.05, and then add 2, you end up with 2.05. This is our answer. Now, does it seem reasonable? Absolutely it seems reasonable. Remember, the square root of 4 is 2, and our answer was just a little bit higher than that, and 2.05 is just a little bit higher than that. I will tell you that if you take a calculator and actually just plug in the square root of 4.2, you'll get that y equals 2.049, and wow, that's very close. If you rounded that to 2 decimal places, we actually got the exact answer. Notice also that our answer, we got 2.05, is just a tiny bit bigger than the actual, and that's what you'd expect again, because the dot, the green dot that we found, is just a tiny bit higher than the red dot, which was the actual value. Okay, this is linear approximation. So to summarize, you don't want to have to draw this graph every time. What you end up with, we're going to give you the formula that gives you this boxed amount every time. For the linear approximation at x equals a, f of x is approximately, very close to, f of a plus f prime of a times x minus a for values of x near to a, right? Have to be close to the a value. Okay, that's what you're going to use to do linear approximation. So let's try another one. Use local linear approximation to estimate the value of the cube root of 26. Now the cube root of 26 is hard. Like, I don't know exactly what that equals. But what I do know is the cube root of 27. I know this is close to the cube root of 27, and the cube root of 27 is 3. So the function that we're interested in this case is the cube root of x. And the a value, which is the value of x we know easily, is that 27. So why don't we write down that a equals 27. So let's look at our formula. What we need to know is, what's f of a? Well, that's no problem. F of a is the same as f of 27, which is the same as the cube root of 27, and the cube root of 27 is 3. So that's good. Next thing we have to know is f prime of a. In other words, we have to get the derivative of x, and then actually we're going to plug 27 in there after. But let's get the derivative first. So remember, cube root of x is the same as x to the 1/3. Let's get the derivative. Bring down the 1/3. X, 1/3, drop it by 1, goes down to negative 2/3. So that's the same as 1 over 3. Flip a negative, comes to the bottom. I'm just going to write it as 2/3, which is the same as 1 over 3 cube root of x squared. Okay, that's f prime of x. We want to know f prime of a. Well, remember, a is 27. In other words, we want to know f prime of 27. How do we do that? Plug 27 in here. So get 1 over 3 times the cube root of 27 squared. Don't do 27 squared first. Do the cube root of 27 first. So you get 1 over 3 times cube root of 27 is 3 squared, which is the same as 1 over 3 times 9, which is the same as 1 over 27. Okay, so now our formula, which could help us get lots of approximations close to the square root of 27, is f of x is approximately equal to f of a, which was 3, plus f prime of a, which was 1/27th, x minus a, which is 27. This is like our magic formula that we can now plug any values we want into x as long as those values are close to 27, because that was our a value, is 27, right? Well, we're finding 26. That's pretty close to 27, so this should work. All we have to do is figure out what is f of 26, and how we do that is we plug 26 into that x right there. So you can get 3 plus 1 over 27, 26 minus 27, that's the same as 3 plus 1 over 27 times negative 1, which is the same as 3 take away 1 over 27, which equals, or I guess I should still say is approximately equal to, 2 and 26/27. And why don't we write that as a decimal? If you do 26 divided by 27, you're going to get 2.963 if we do it to 3 decimal places. And this is our answer. Want to know the actual? I'll put the actual to 4 decimal places. And if you go to 4 decimal places, you'll get 2.9624. Again, very, very close to the actual answer. Okay, a couple more. Find the linear approximation of f of x equals x cubed minus x about x equals 1, and use it to estimate f of 0.9. So when it says about x equals 1, this tells you right here that your a value is 1. And you know your f of x, obviously. F of x equals x cubed minus x. And what we need to know is we need to know what f of a is, and f prime of x, we need to get the derivative, and once we've got the derivative, we've got to find f prime of a. Basically, these are the two big ones you need right there, f of a and f prime of a. So f of a, well, that's no problem. We already said a is 1, so this just means we need f of 1. We're plugging 1 into this function, so that would be 1 cubed minus 1, that's 1 minus 1, which is 0. Okay, now we get the derivative of that function. No problem there. Power rule, 3x squared minus 1. Okay, now what we want to do is we want to get f prime of a. This is just the derivative, but I want to know what that derivative is equal to at this particular point a when it's 1. So f prime of 1. So plug 1 into here. You get 3 times 1 squared minus 1. That's 3 times 1 minus 1, which is 2. Okay, we're ready to plug it into the formula. Why don't I just plop the formula up here again. Okay, so let's find our master formula first that would work for lots of values that are close to 1. Well, f of a we said was 0, that's nice, plus f prime of a we said was 2, and then we have x minus a, and a is 1. So we can simplify this a little bit. F of x is approximately equal to 2. You could expand this if you want, but I'll just leave it like this. And there you go. This formula right here will give us approximate values as long as our value we're interested in is close to 1. In this case, the one we're interested in is 0.9. So this will be no problem. We're going to do f of 0.9 is approximately equal to 2 times 0.9 minus 1, which is approximately equal to 0 times negative 0.1, which means it's approximately equal to negative 0.2, and that's our actual answer. Still interested in the actual? Well, it's not quite as good this time. The actual this time would have been negative 0.171. But hey, if you round it to one decimal spot, you do have the right answer. But when you look at 3 decimal spots, not quite as impressive. Okay, finally, given the equation 3 times x squared plus y squared minus 100xy equals 0, use local linear approximation at 3, 1, the point 3, 1, to estimate f of 3.1. So what you'll notice here is you have lots of x's and y's here. You're not going to be able to isolate those y's. So what does that mean you have to use? You need to use implicit differentiation in this question. Okay, so remember, we need 2 things. We need a point, which we already have, and we need a slope. This is how we're going to get that tangent line, right? And like in the drawing we did before. And to get the slope, we need to get the derivative of this equation right there. And that's where the implicit differentiation comes in. So this first part right here, you're going to have to use the chain rule. So let's do that first. The 2 comes down and multiplies the 3. You get 6 x squared plus y squared, and then that 2 drops to a 1. That's the outer function. But then you need to multiply that by the inner function. So for the inner function, you take the derivative of x squared, which is 2x, and the derivative of y squared, which is 2y, but in terms of x. So you also have to put y prime. Great. Now, we're going to find the derivative of this bit. For this part, you're going to have to use the product rule. So, to start that, we take the derivative of negative 100x, which is negative 100, times y. That's the second part of that piece here. Then you're going to add to that the first piece, which is negative 100x. Well, why don't I just change this to minus 100x then, because I'm adding a negative. So minus 100x times the derivative of y. Derivative of y is 1, but it's in terms of x, so you have to put y prime. And that equals, the derivative of 0 is 0. Okay, so now what we're going to do is, this is what the slope is equal to at that point. But in order to get exact value, you've got to plug 3 into the x's and 1 into all the y's. So we'll do that now. 6, 3 squared, that's 9, plus 1 squared, that's 1. 2 times 3 is 6. 2 times y is 2, and we still have a y prime. Minus 100 times 1 is 100. Minus 100 times 3 is 300. Y prime equals 0. And let's isolate the y primes. So how will we do that? Well, we add the 9 and the 1, get 10, and multiply by 6, we get 60. 6 plus 2y prime minus 100 minus 300y prime equals 0. Let's expand this out here. So you get 360 plus 120y prime minus 100 minus 300y prime equals 0. Combine the 360 and 100, minus 100, you get 260. Combine the 120 and the minus 300, you get minus 180 y prime. Why don't we move the 180 over to the other side, so you get a positive 180 y prime. And the last thing you have to do here before we simplify is to divide both sides by 180. So you're going to get 260 over 180. Could knock off a 0 there and get 26 over 18. Divide them both by 2, you get 13 over 9. So this is our slope. So when you have a point and a slope, and you want to get the equation of the tangent line, you can just use the point slope form. So we're going to go y minus y1, which is 1, equals the slope, which is 13 over 9, times x minus x1, which is 3. And we'll just move that 1 over. So we get y equals 13 over 9 x minus 3 plus 1. So again, this is our very useful equation here. If you have a x value that's close to 3, you'll just plug it in here, and then it'll give you an approximate y value, a very close y value to the actual amount. Well, the x value we have is 3.1, so this is going to work very nicely. We just have to put 3.1 into that spot right there. So we get y equals 13 over 9, 3.1 minus 3 plus 1. Y equals, I'm going to keep it as fractions this time. I know it's kind of weird, but I'm going to do that. 3.1, take away 3 is 0.1. You know what 0.1 is as a fraction? It's 1/10 plus 1. So I get 13 over 90 plus, well, 1 is 90 over 90. So I end up with, whoops, that's 90 over 90. So I get 103 over 90. And remember, this is all approximate. I should be having approximately, all those things. So it's approximately equal to 103 over 90. And if you divide that on your calculator, you'll find that it's equal to 1.14 to 2 decimal places. Okay, there you go, local linear approximation.